Okay, thank you everyone for joining us this evening. This is the second part of our three-part webinar series entitled Get the Dirt on Your Soil, where hopefully you will learn all things soil. Tonight, we will be having Dr. Stephanie Murphy, the director of the Rutgers Soil Testing Lab, talking to you about soil testing, what the soil tests tell you. So basically digging deeper in what is your soil telling you. So if you do a soil test, how to interpret the information, etc. My name is Steve Yurjo, and I am the Agriculture and Natural Resources Agent with Ocean and Atlantic Counties. And we are happy to have you all with us this evening, for tonight's webinar. Just a couple of housekeeping things. We are recording the webinar tonight, and we will be making it available on the Agricultural Experiment Station's YouTube channel. I will be sending out an email to everyone letting you know when it's available in just a few days. So I ask for your patience in getting a couple of days of getting this set up and uploaded, etc. For those of you who've come to our webinars before, welcome back. For those who haven't, we will be taking questions, but at the end of Dr. Murphy's presentation tonight, if you have any questions, feel free to put them into the chat. Make sure that you send it to either all panelists or everyone, or if you want to just keep it private, send it to myself, but it's good for people to see what kind of questions are being asked so that we can get them. If you do not know where the chat is, it's either on the bottom of your screen or on the bottom right. On the bottom right, it will say chat next to what looks like a cartoon word bubble that should be filled up with words, but it's empty. Or if it's at the bottom center of your screen, you can probably just see a button that looks like just the word bubble. So if you click on that, it will open up the chat on the right side of your panel or your screen or whatever your device you're watching on. And you should be able to type in to the panelists what your question is. You can also use another feature. It's called the Q&A. So it's a question and answer. That is also found on the bottom right or on the bottom. Usually you have to press a button that has 3 dots in it to get more options where the Q&A is. Click on that, and then you can type in your question, and we'll be monitoring that to answer towards the end. So once again, we will be handling all the questions at the end of the presentation tonight. Like I said, we are recording this, so if you missed something or want to see something again, you'll have that opportunity. But it is my distinct pleasure to introduce Dr. Stephanie Murphy tonight. We appreciate her taking the time to do this. She's very busy this time of year, and in the spring that's usually when we ask her to do these kinds of talks. She's the director of the Rutgers Soil Testing Lab, and she knows all things soil testing, and she'll be talking about soil testing and what you can learn from it. And that is my spiel. The last thing I will say is that in 2 weeks, we will have the third and final part of the Get the Dirt on Your Soil webinar series, where I will be talking about soil compaction and how you can root out soil compaction, what it is, what you can do about it, and how you can prevent it from happening in the future. So that's Thursday, October 8th, same time at 7 o'clock. So thank you again, Stephanie, for doing this, and you are good to go.
Okay. Thanks, everybody, for being here. It's my pleasure to try to share with you more about soil, digging deeper into soil. And if you were at the first part of the seminar series, you learned some about what exactly is soil. So just as a little bit of review here, we want to point out that the components of soil are shown in this pie chart here. These are volume percentages of the components of soil. And you see here that approximately 50% of the soil volume is made up of solids, mostly mineral material. You see about 45%. And the remaining solids will be organic matter, organically derived materials from organisms. And notice that the other 50% of the volume of soil is pore space, and it's filled in varying proportions with the soil solution, that is the water and anything that's dissolved in it, and air. So those two components are constantly changing in proportion in the soil. But we recognize that that's what makes up soils, but realize that soil and that They are variable both with depth and across the landscape. So we have changing conditions of soil, changing characteristics of the soil, both across the landscape and with depth. And those characteristics that you would find in a specific soil type are dependent on the 5 soil forming factors. And Becky mentioned these last week, that you start with different types of parent material, the geologic parent material that are acted upon by the climate, various climatic forces, and also the organisms that live in and above the soil. Topography has some effects in terms of drainage or susceptibility to erosion and sedimentation, for example, as well as microclimate effects. And all of the changes are happening over different periods of time. And so that's what creates the variability in the soil, again, both across the landscape and with depth within the soil. So here's some examples of different soil types, the cross sections, so that you can see the depth soils and how the soil characteristics change with depth. And so there's different mineralogies of soil particles, the inorganic fraction, different degrees of weathering, different amounts of organic matter and rates of decomposition, drainage conditions, and so forth. So soils are very variable across the state and across the country and globally. And so that's something obviously some of you recognize already. You've mentioned what your soil type is like in your county or in your particular area of the state. And so we realize that with that variability then comes different management perhaps, or different conditions that we need to try to manage to optimize them. One of the curious things about the definition of soil is that a definition of soil often includes reference to soil as a media for plant growth. The Soil Science Society of America, for example, says soil is the unconsolidated mineral or organic material on the immediate surface of the earth that serves as a natural medium for the growth of land plants. Okay, and so on the left there in the diagram, you see all the interactions between the plants and the soil, and nutrients, water, organisms, air, and so forth. Another definition that I have a fondness for is the idea that soil is a link between the rock core, the hard rock core of the earth, and the living things on its surface, or the biosphere. So you have the rock, the inorganic rock, and the biosphere, and what's in between soil. And so how important is that for all of life on Earth, right? And plants are primary producers on the land. Okay, so most other types of organisms in our ecosystems ultimately depend on plants as their source for carbon or energy. Right? It all comes back to plants as a primary producers. So what does soil provide that helps it serve as a media for plant growth? Well, partly just the physical support of the plant. It anchors the roots and it holds that plant upright so that it can reach upwards towards the sun, right? In the pore space, we just reminded ourselves that the pore space holds water. It stores water for those plants necessary for their growth and action. And also the gases, gases is very important for the roots that are living underground. And of course, the soil is a bank of nutrients for the plants. And that's what we'll be mostly focusing on today. So the soil in your landscape, I'm assuming most of you are interested in soil because of its support of your landscape plants in a residential type setting. So how can we manage our soil conditions to optimize it for your landscape plants? And what are the most sustainable operations or management that presents the least hazard to the environment? And of course, we'll be interested also usually in what are the low input options, whether it's a matter of dollars, how much we put into our management, or think about conserving water, or our own time and effort. Okay, so what are those low input options? Now, the soil, when we talk about it as a bank of nutrients, we need to think about what we mean by the nutrients. Well, essential nutrients are those elements that are necessary for the growth and reproduction of the plants. The plants, some of the major nutrients, the needed in the most amount are actually carbon, hydrogen, and oxygen. And the plant does get those elements from air or water. But all of the other essential plant nutrients come from the soil. Okay, and so that's the table that you see on the right there. All the elements, well, and this isn't even a complete list, but some of those essential nutrients that come from the soil. Nitrogen, phosphorus, and potassium are needed in relatively higher amounts. We usually call those macronutrients, just because, again, we need them in larger amounts in the plant. Calcium, magnesium, and sulfur are sometimes called macronutrients, but sometimes, because they kind of transition to lower amounts necessary, are sometimes called secondary nutrients, whereas copper, manganese, zinc, boron, iron, molybdenum, and so on, anything else, are called micronutrients. They're needed in very small amounts. They're still essential, but just needed in smaller amounts in the plant. And what do I mean when I say essential? Well, those elements are either needed in the structural parts of building the plant, or in the metabolism of the plant. And so obviously I'm not going to read line here, explain what each of these individual essential plant nutrients do in the plant, but just to point out that there are specific purposes for those different elements within the plant, and that's what makes them essential for the proper functioning, proper metabolism and growth of the plant. And when a plant doesn't get enough of those elements for the proper growth, you will see deficiency symptoms that reflects the dysfunction of the metabolic processes that require that missing element. Okay. If there are low to moderate deficiencies, you may not see a visual symptom, but still there would be less optimum conditions and therefore less growth or because of the missing element, the missing nutrient element. Okay, so soil is an operation that we can do to determine the conditions of the soil and therefore what's needed to optimize the plant health or growth or yield in some cases, right? So, otherwise we're working blindly. If we don't know what our soil conditions are, we don't know what to apply and what amounts to apply, for example. This graph shows the relative growth of a plant in response to changing concentrations of the nutrient in the plant tissue. So you see at very low concentrations of a particular, this is just for one individual element, nutrient element, at very low concentrations, you see the growth curve is very low, shows low plant. That's in the zone that's called deficiency symptoms. So there, the concentration is probably low enough that you would actually see a symptom in the, visually in the plant. As you increase the concentration of that nutrient, the plant growth improves. And you may know, it may be possible that you don't see a deficiency symptom any longer, but still the plant growth isn't to its optimum capability. And so that's what we call hidden hunger. Eventually, if you continue increasing the concentration, you'll reach that critical range. Okay, and that's just meaning the point where you're reaching the optimum level of the nutrient for that plant at that stage of growth. And then there's a plateau where that level, you can continue to increase the concentration of that element, but it doesn't continue to increase the growth of the plant. And so that's the optimum range or the sufficiency range. And you see on the other end of that, then, if you increase the concentration too much or to a even higher extent, the plant growth can actually decrease. So we have to understand that relationship and try to manage our soils so that the plants are in that sufficiency or that optimum range for the growth and health of the plant. So if the plant nutrient is deficient, the plant is not achieving its full GD. You may see the deficiency symptoms, or you may have hidden hunger. But in that case, the management strategy, as you see in the graph, if you're below optimum in the soil fertility level, we want to try to build up that nutrient level within the soil. If we're in the adequate or sufficient range, that means that we're at 100% growth potential of the plant, assuming that everything else is satisfactory. It's not limiting the growth of the plant. And so we want to try to maintain that level, that plateau where everything is optimum. But we can get to that level again of where we have excess amounts of the nutrient, and it can create imbalances or toxicities even that will decrease the growth of the plant. And in that case, we want to apply no or very little of that nutrient element to help draw down the concentration of that nutrient in the soil and in the plant to try to achieve the optimum condition. Another thing that's very important in soil or plant nutrition is soil pH. And just as a quick reminder of what soil pH is, the pH scale goes from 0 to 14 with a pH 7 as being neutral, okay, right in the middle. That implies there's a balance between the hydrogen ion that represents acidity and the hydroxyl ion, which represents alkalinity. So if you get more hydrogen ions in the solution, it becomes more acidic. The value, the pH goes down, and that's considered acidic. Whereas if you get lower amounts of the hydrogen ion, the value of pH goes up, and that's considered alkaline. More acidity means a lower pH, in other words. Okay, and as you see, the soil pH is an important plant growth factor that we can manage. For most plants, the optimum range of soil pH is between 6.5 or maybe up. But there are certain plants that have a preference or are more adapted towards lower pHs. For example, 4.5 to 5.5 would be a typical range for many ornamental landscape plants like rhododendrons and azaleas, hollies, Some of the plants that are native to our coastal plain, right, where the soils are naturally very acidic, will tend to have a pH preference in that lower range. So we do have to know our plants as well, and try to, in order to try to optimize the soil for those conditions. Now you see on the diagram there the different soil ranges of pH. Most of the soils in New Jersey were under forest at one time, right? So it might range from 4 to 6 possibly. But on the other hand, we've had agriculture in this area for hundreds of years. We realize that we've been liming the soils, and therefore we do tend to have some higher pH soils up to possibly 7. And if you live on a limestone ridge in the valley and ridge area of the state, you could actually have pH 7 or possibly a little bit higher than that even. In New Jersey, we do also have these acid sulfate soils. Ideally, they are buried sediments and stay buried, and we never have to see them. But if they do get exposed to air, either through erosion or excavation, development and so forth, those acid sulfate soils or those sediments can become acid sulfate soils where the pHs can go down to 2 or less. So ideally, you'll never see that. But just to point out that acidifying processes are natural in the soil. There's a number of different processes mentioned here that tend to make the soil more acidic. Whether it's the production of carbonic acid from CO2 in the soil atmosphere, or the organic acids that are released by the organisms in the soil. Some of it's the leaching of the basic cations. Okay, we have enough rainfall in New Jersey that there's leaching to the groundwater, and that might carry some of these basic ions down to groundwater and remove them from the soil, leaving behind more acidic conditions. So that tendency is for our soils here to become more acidic. So what do we do to try to manage that? Well, applying limestone is the normal response and operation for management. But how much and what kind? Sometimes soil pH is higher than optimum. Again, if we're growing some of those acid-loving plants, we may need to acidify the soil to create the optimum conditions. So how do we do that? We need to understand where we are in the soil pH. And why is soil pH important? Well, this graph is a great example of how soil pH affects the nutrient availability. Okay, on the top of the graph here, you see a pH ranging from 4 to 9, which covers most soil range. And you see the different elements there, starting the third bar down is nitrogen, potassium, sulfur, and so forth. So the width of relative availability of the nutrient at that given pH. So you can see, for example, that nitrogen becomes less available when the pH drops below about 5.5. You'll notice in particular the phosphorus line, the one that's marked with a P. It is at its maximum between pH 6 and pH 7, and below 6 and above 7, the availability of phosphorus decreases pretty dramatically. And so that may be one of the reasons why pH 6 to 7 is often cited as an optimum pH range for most plants. Okay. But you can see some of the micronutrients, iron and manganese or molybdenum, are strongly affected by soil pH, and sometimes in opposite directions, right? So we need to find that perfect balance of pH to make all of these nutrients available for the plant. Also, we'll point out that Aluminum is indicated on this graph, and aluminum is not a nutrient element, and in fact is toxic to plant roots. So that we see that below pH 6, increasingly aluminum becomes more and more soluble or more and more available, which means more toxic to roots. So that's another reason why soil pH is really critical for the health of our plants. The concept of the limiting factor tells us that plant production is constrained by the most limiting growth factor. And these essential for each possible limiting growth factors, okay? In the diagram there, the staves of the barrel represent these different factors, whether it's a nutrient element or other potential limiting factors like light or water availability or soil temperature or oxygen, okay? So in the barrel on the left, we see that nitrogen is the limiting factor, the limiting growth factor. The growth, in this case, represented by the level of water or whatever that green stuff is in the barrel. I like to think it's chlorophyll. You get better growth. Growth is limited by nitrogen, by the length of the nitrogen stave. Right? On the right-hand side, you see that phosphorus is the limiting nutrient. Okay, so in that particular case where phosphorus is the limiting nutrient, does it make any sense to apply nitrogen? Okay, so our corollary here is that increasing the non-limiting factor will not improve production. We have to know what it is limiting production before we can correct the problem. And trying to pour more nitrogen on to try to solve a phosphorus problem can only make things, complicate things and possibly make things worse. Soil pH and the nutrient levels in the soil. Soil testing provides the answers. It gives our nutrient values and the interpretation of those values. And based on that, fertilizer recommendations. It gives you soil pH values. And based on that, if you need limestone, we will give lime recommendations. And there are other soil tests available as well, such as organic matter content or soil textural analysis, and so on and so forth. We offer quite a few tests at the Rutgers Soil Testing Lab. So hopefully you have a good sense of why we need to do soil testing to manage our plants properly. But how, what does this all rely on? Soil testing relies on an accurate laboratory analysis. Okay, so at our laboratory, we get the best equipment that we can afford, and we do everything according to standard methods, defined by, for example, the Soil Science Society of America. And, everything that we do in the lab, try to get the most accurate results for your purposes of managing your soil and your plants. But it also requires a lot of prior research, okay, to calibrate that data that we're getting in the laboratory to what plants' response is in the field or in your, in your landscape, so that we can make the proper recommendations based on those data, okay? But also, to go back to the beginning of the whole process, soil testing relies on a good soil sample. Okay, and that is on you. Okay, we rely on you to take a good soil sample and submit that for testing. The data and the recommendations could be worthless or even harmful if the soil sample isn't taken properly. You may remember the old saying, garbage in, garbage out, right? So the goal of soil sampling is to obtain a representative sample of the appropriate zone in order to analyze its properties and then determine how to optimize the growing conditions or diagnose a problem based on that data. Okay. So when I say we want to get a sample of the appropriate zone, what exactly do I mean by that? Well, remember that soil is a three-dimensional body, so we have to think about the area that we're sampling and as well as the depth. So the area of interest is going to be a defined area that you have to define depending on soil type, for example, the type of plant that's being grown, and possibly past management, the history of what's been applied there in the past. If there are any differences across a particular area, then you would want to divide that area into more sections depending on what those different factors are. Okay, in some cases, you might divide it simply based on a problem. You see a problem and you want to know how does this particular problem area differ from where the plants are growing fine. And in that case, it's pretty well defined what your area is. But remember again that depth component. So 6-inch depth is generally what we recommend. That usually covers the whole vast majority of the root zone for most plants, since roots are really concentrated near the surface. And also just modification of deeper soil zones aren't really expected to any great extent. If you're applying things on the surface or even if you're mixing them in, it's hard to treat what's below that depth unless you're really getting into deep tillage. When I'm talking about different types of plants, these are the different categories that we use on our soil test questionnaires, the forms that you fill out to send with your samples. So cool season grasses, for example, are treated and managed differently than warm season grasses, and so they would be separated out as different areas. Annual flowers and perennial flowers, besides the fact that they're usually grown in a bed that has different amendments, they also take up different types, different proportions of nutrient and return different amounts of nutrients to the soil and so on. So take into account the different types of plantings when you're trying to decide your sampling area. Of a yard or property, I should say, and it's showing a house there. We're looking down at it from the sky, and so you see the house and a driveway, little deck on the back of the house. You have area 1A and 1B are lawn areas. 1A has a lot of trees in it. Area 2 is representing a vegetable garden. 3 is a rose bed, and area 4 is an acid-loving species bed. Okay, so there's different areas that you could delineate as being separated for different samples. Okay, you shouldn't, for example, take a sample from area 1B and use those recommendations in area 4. Okay, it's not appropriate. Your samples should be separated. And this is a totally different type of area, but if we look at this lawn here in New York City, and we were going to sample this area, we would want to consider that any one of these starred areas may be different from the other. Even though it's all been treated the same, it's all been lawn area for many years, but there might be slight differences at each of those spots within that lawn area. So a representative sample is a composite of many subsamples taken throughout the area, okay, to average out those within that area. So the idea here is at each of those points that I've marked there might be a sampling point that we would take a subsample to combine all those subsamples together and homogenize to represent that whole area. Okay. You know, if we could, we would take the whole root zone and analyze the whole root zone to get an accurate representation. But obviously we don't want to do that. But we do want to try to get an average for that entire area. Consider that, you know, that whole area, when we actually do the testing, is going to be represented by a very small subsample that we use to extract. And so we want to make sure that that subsample is a good representation of that whole area. And again, you do that by taking many subsamples and combining them together. How many subsamples should you take? Well, it depends on the total area that you're looking at. If it's a small area, say less than 100 square feet, maybe 5 subsamples is a good suggestion for number of subsamples. But if you have more than 100 square feet, definitely go up to at least 10 and maybe 15 subsamples. And again, just increasing the number of some subsamples depending on the actual size of the area. Okay, and again, we want to break up those subsamples and homogenize all that soil together. Okay, and then from that, taking out the certain portion that you're going to send to the soil testing lab to represent that area. So back to this diagram here, we're sampling just that lawn area 1B, and so we're wandering through that lawn area and taking a subsample at these different points, combining those subsamples together and to send to the lab. Now, if you have a soil probe, that makes it really easy. It's just a tube with an opening on the end that you can push into the soil and get a core. And again, we would try to get to 6 inches ideally. If you don't have a soil probe, and not many people do, but you can still get a sample using a trowel or a shovel. The idea is just to take a slice of the soil. You can dig a hole down to 6 inches and then take a slice from the side, trim off the edges so that you have basic core, in this case kind of a rectangular core, and that can be your subsample. Okay, and then when you have your 10 to 15 subsamples, for example, and put them into a clean bucket, homogenize those subsamples, and from that, once it's homogenized, take out 2 cups approximately to send into the soil testing lab. I've shown it here, putting it into a paper bag, but ideally a plastic bag is a better choice to send the sample in. We have soil testing kits available at most of our county cooperative extension offices. Unfortunately, right now, because of the pandemic, you cannot get to a cooperative extension office to get a soil testing kit. However, we do have all our sampling instructions online on the soil testing website, and we have the question that you would send in with your sample, the paperwork. Send in with your sample. On the upper left-hand side there, that shows what a soil test kit is, and it's basically the sampling instructions and the soil test questionnaire, along with an envelope that you put the questionnaire back into after you filled it out, attached to a canvas bag with a plastic bag that you put the soil sample into. And you can see on the right, we've received thousands over a year. We receive thousands of these like this. Don't be tempted to tear the envelope away from the bag. If you do happen to have a soil test kit, you can send it in the mail just like you get it. But as I said, right now, you'll have to go to our soil testing website to read the sampling instructions and to download that soil test questionnaire, and then just put it in your own packaging to send the sample to us. Okay, and this shows the process of logging those samples in and assigning them a lab number. In the laboratory, we have the sample preparation is basically sample in a box, a chipboard box to dry. We put it in a ventilating cabinet to help speed the process of drying. And then it goes through a grinding process to break down any aggregates and a sieving process to remove gravel and any of the organic materials like roots and grass and so forth. We do the extraction procedure to get the nutrients, and we do the soil pH analysis. All that data goes into to be generated into a report. So just here's some more picture preparation stage where we're putting it into a sample box. You see the samples before they're ground. You can see some of the granular nature of it before they're ground and sieved. And then in the lower right hand, you see the samples after they've been sieved, and just a variety of sample types of samples that we get. This is a matter of adding a very small sample of the soil. You see there going into those flasks there on the top left picture, and we add an extracting solution. It's composed of nitric acid, salts, and a chelating agent. So it's a very harsh chemical extractant that is intended to displace the nutrients that we want to analyze from the surfaces and put them into solution. Okay. And as I mentioned before, the interpretation of those values are based on prior research that's been done in the field to calibrate the plant response to fertilizer applications or yield, for example. The extracts then go into an instrument that's called an inductively coupled plasma spectrophotometer. Again, I said we try to use the most advanced equipment that we can afford. This is an atomic emission technique where each of the elements is emitting a spectrum, and we pick one wavelength from that characteristic spectrum to analyze the intensity to help us to quantify the amount of that element in the extract. So that's what we use for quantifying the amounts of phosphorus, potassium, calcium, magnesium, copper, manganese, zinc, boron, and iron. And I'll just show you that as one example, why it's important that you know what soil extractant is being used. There are different extractants that are used, and phosphorus is the one that shows up the most differences. But you can see with these different named extractants that each of them will extract different amounts in a different range of phosphorus from. We use that Malic 3 extractant, and it extracts a wide range of phosphorus, which helps us to kind of better quantify or interpret the value of phosphorus in your soil. So just keep in mind that you can't always compare results from one directly to results from another lab, because it does depend on what extractant is used. But ideally, we would all use a similar, we would also all come to a similar conclusion as to the relative amount in terms of whether it's deficient or optimum or above optimum. So once again, we see this type of graph where we're looking for that critical level, and where the soil test level value is given on the bottom axis and the plant response on the side axis there. So we want to try to get our soil test level up to that optimum range. Okay, and this just shows some real data that might have been used to determine what is that optimum range and what is that critical value that we want to be above. The other test that we do, as I mentioned, is the soil pH. We do that with a one-to-one soil water suspension using an electronic pH meter, and the data is fed directly into the computer. We also measure what we call the buffer capacity of the soil, and that is important for determining the limestone recommendation. The buffering capacity of the soil depends on a couple factors, one of them being the soil texture. And if you remember, soil texture is the percentages of sand, silt, and clay, different size fractions in the soil. And so if we have a very sandy soil, for example, the soil tends to be poorly buffered. Okay, that means it's easily changed. Whereas if you have a very fine textured soil, it's going to be highly buffered. That means it's harder to change. Okay, and that it's not only in terms of pH, but also nutrient levels. That tends to be true as well. So that's why we need to understand what that buffering capacity is to determine what the lime requirement is. So not only do we need to know the pH change desired, okay, how many pH units do we need to increase, but we also need to know the soil's buffering capacity. So if we have a very sandy soil that's poorly buffered, we may not need a lot of limestone to raise soil pH. But if we have a highly buffered soil, it can be the same pH that we need, but because it's highly buffered, we need that much more limestone to make that change happen. Okay, and this graph just shows what happens when we do add limestone. Soil pH increases. Notice that it does take a period of time. It's not an instantaneous change. So, you know, do it well in advance, or just don't expect, you know, immediate. It can take up to a full year depending on the materials that you're using, the characteristics of the limestone. But you see what I mentioned earlier, that over time, the pH change does tend to re-acidify. Okay, it's just the natural processes that occur in the soil. So we may have to make repeated applications, but we don't want to make them too frequently or in too great amounts to create very alkaline conditions. And I have seen that in samples where people routinely apply limestone, but without benefit of a soil test. So this is what a soil test report might look like. Again, we give you the data, the soil pH and the nutrients in the basic fertility test. We interpret the values both verbally and with graphs, as you see here. And we do give recommendations: limestone if you need it, and fertilizer. So here's example for the pH. You see the value there, the bar graphs with the red, green, and yellow. The green representing what is the optimum range for the specified plant. And the little arrow is showing what the pH is for that particular sample. And so based on that, in this case, there would be limestone recommendations to try to raise that pH into that green zone. The lime requirement index, again, is just our measure of the buffering capacity, and it helps us to calculate how much limestone for you to get into that green zone. We give the macro and micronutrients both in terms of pounds per acre, so an actual value, and on the bar chart there you see as either below optimum, optimum, or above optimum. And here's some examples of recommendations for limestone. Okay. It tells you what the optimum range is for crop. In this case, we have both turf grass at the top, and further down, the secondary crop was a tree. And so we tell you what the optimum range is, and then the recommendation for limestone to get to that level. We also are looking at the calcium and magnesium values to determine what type of limestone you need to apply, ideally, to get that pH and also correct the magnesium deficiency. Now, nitrogen is not included in routine soil fertility. It's often a surprise to our clients, being that it is one of the most important fertilizer nutrients, right? But so why is that? Well, you see here the nitrogen cycle. It's a very with a lot of different possible inputs and losses, very many transformations, some of them biological transformations within the soil. And so it's hard to keep up with it. It's a very dynamic system, changing constantly, and even on a day-to-day basis, you can get different values because of all these processes that are going on. So the amount in the soil may have changed by the time that we actually complete an analysis. So it's not a good basis for making a nitrogen recommendation. Okay, so instead, you get recommendations based on the seasonal needs of that particular crop. And just as an example, here's two examples, well, actually three, the cool season grasses versus the warm season grasses. You see they have different growth cycles related to the season, and they have specific nitrogen needs that correspond to their growth stages. And so your nitrogen recommendation is going to account for that and give the nitrogen in the amount that's needed at the proper time of year for it. And the other example is tomato there. So you see the different growth stages, and at different periods of the plant's growth, it's going to need that nitrogen. And so your recommendation is going to give you a recommendation for nitrogen to correspond to the plant's growth cycle. Okay. A recommendation, notice that for fertilizer, notice that we give the ratio of nutrients that are needed, not an actual analysis of fertilizer, and we don't, name names of fertilizers, but we tell you what the plant needs in terms of its nitrogen, phosphorus, and potassium, and you have to go out and search for the appropriate fertilizer. Okay, so, and we tell you how much nitrogen. So if you find this correct ratio of the fertilizer product components, and you apply it at this particular rate for nitrogen, you will automatically be applying the right amounts of potassium and phosphorus. In this case, there's no phosphorus recommended, but if there were, you would get that as well. If you can find it in the correct ratio of nutrients and apply it at the rate for nitrogen, you'll get all the other elements proportional to it in the correct amounts. Now, I just wanted to throw in the phosphorus cycle here, and notice it's much different than the nitrogen cycle. And so these are things that you have to understand how the biogeochemical cycles work to fully understand the nutrition for plants. But with phosphorus, it tends to be relatively insoluble and low availability in soils. Even when you do have minerals in the soil that have phosphorus in them, tends not to be a very solid element in the soil. And notice that also when phosphorus gets into waterways, it can be a pollutant. Okay, really getting to the end here, so I'm speeding through. Potassium is another thing that I want to say about potassium is notice that there is no organic matter fraction in the potassium cycle. When plants decompose, even though they may have significant amounts of potassium in them, remember, they're not combined into an organic molecule. So they don't, the potassium doesn't exist in the itself. It leaches into the soil, could be immediately available for take-up, but also could be subject to leaching, for example. So again, you just have to understand these different cycles to get a good understanding of plant nutrition. Fertilizers, NPK analysis, we use that term NPK, but I want you to recognize that the percentages are actually, for nitrogen, it is percent nitrogen, but for phosphorus, it's expressed as the oxide, PTO5, so it's percent PTO5, not actually P. And for potassium, it's percent K2O, not potassium. Just to be clear on that. So when we're doing calculations, we have to keep that in mind. The label for you to understand, and that's really what you should be basing your purchase of fertilizers on, is that NPK analysis. Okay, don't be, lawn food or rose fertilizer. What you really need to know is the NPK analysis to choose the right type of fertilizer. Okay, so jump through this a little bit. We do also give interpretations for the micronutrients, but the recommendations are much more general. We do refer you to the fact sheets, the Rutgers Cooperative Extension fact sheets that cover those micronutrients more specifically. Okay, but we do give you just a general couple of statements about those different elements. What if I apply too much? Okay, for plants, an excess, as we saw, can be just as bad as a deficiency. There is the potential for imbalanced nutrients. So just like in a human body, we can get imbalance of nutrients that can cause health problems. And so the same is for plants. You can create these imbalances and induced deficiencies. So the chart on the right shows that there's antagonism where there's the solid lines between the different elements. That means there's an antagonism between take-up of those different elements. So if you want to learn more about that, search for Mulder's chart, and you'll be able to see that a little more clearly. But just so you understand that, that there is such a thing as too much. You can also create toxicities in some cases, or create a salt hazard. If it's a very soluble fertilizer, for example, you could burn your plant roots or even the leaf tissue if you're applying it on grass, for example. You can burn the tissue if you're applying too much. And that can sometimes also, having too much fertilizer can make the plant more susceptible to disease or insect attack. Along with the environmental risks. So I mentioned way back at the beginning about sustainability and our concern for the environment. So realize that applying too much fertilizer can put our water bodies at risk from nutrient pollution. So the term eutrophication, probably you've heard of before. In ecology, it's it means characterized by an abundant accumulation of nutrients that support a dense growth of algae and other organisms. Okay, so you're supplying a nutrient that allows a flush of growth, and then when it starts dying and decaying, it depletes the body of water from oxygen, which then can cause death of aquatic organisms. So eutrophication is basically nutrient pollution that causes algal growth and depletion of oxygen in the water. So in fresh water, phosphorus is usually the problem nutrient, and in salt water, nitrogen is often the problem nutrient. Okay, and just as an example here, we see some photographs of eutrophication of some freshwater bodies like Lake Erie. Yeah, I guess all the other examples are saltwater bodies. Gulf of Mexico, zone of hypoxia, or the dead zone. And then we have a couple pictures on the coast of New Jersey that shows the same thing. Okay, I have reached 8 o'clock, so I can stop there.
I did mute myself for a second there. Stephanie, thank you so much. As always, full of good information and very informative. So I really appreciate that. So if you have a few minutes, we can go ahead and get to some of the questions. If you want to just take a break while I'm sitting here talking, because I know you had a class earlier today. But I will go through I will go through some of the questions and ask you. One of the things that